Hello everyone, welcome to Technologies Discussion channel. Today, I'd like to continue the discussion on impedance matching. For this video, I'm going to illustrate an example. How can we actually design a single stub shunt tuning for impedance matching. This example, I will be using Smith chart to design the single stub shunt tuning for impedance matching. This will be the part 10 series discussion on impedance matching. So if you're keen to know more about impedance matching, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on impedance matching. Guys, please also take a look on the Smith chart. I have also put the Smith chart playlist under the description. Over there again, you will have more information regards how to plot on the Smith chart. This is my email. If you have any question regards on this discussion, please drop me an email. Before I continue, I'd like to urge you guys to support this channel by pressing the like and also the subscribe button. Please also turn on your notification bell in order to receive more information from this channel. Guys, once again, thank you so much for your strong support. Before we go into the example, let me quickly describe what is actually a single stub matching. In short, this single stub matching can be configured either as a shunt stub or a series stub. And on the shunt stub, basically it can be open or short circuit. As for the series stub, it can be also either open or short circuit stub. So let's understand a little bit more regards on this single stub. Okay, in this single stub tuning, the two adjustable parameters are the distance D. Okay, you can see that this will be the distance D. Okay, what is distance D? Distance D is actually the distance from the load to the stub position. Okay, for example, this will be the stub position, and the distance D, in fact, will be the separation between the load and the stub position. Same for the series configuration. So this will be the location of the stub, and basically the distance D is in between the stub and also the load. Okay, another thing that we can adjust will be the value of substance and also reactance that is provided by the stub. Okay, let's focus on the shunt stub first. Okay, for this particular case, which is configured as a shunt stub, okay, the basic idea is to select D so that the admittance Y seems looking into the line at a distance D from the load is actually has this form here. So which means that when I actually look over here, I actually will have this form. Okay, so once I have this form, you can see that in order to be matched, I just need to cancel away this JB. Okay, so then therefore the stub substance is actually chosen as minus B. And when we actually do this, it actually result in a match condition. Now let's take a look on a series stub scenario. For series stub scenario, okay, the distance D is selected so that the impedance Z looking into the line at the distance D from the load, okay, is of this form. Okay, so when I actually look at the position of the stub, okay, basically they will be configured at this form. And from here, if you can see that if basically I have this reactance as minus JX, I will be basically cancel away and this term will be matched. So the idea is basically the stub reactance is basically choose as minus X. So therefore, this will result in a match condition. Okay, I guess with this, you have a better idea. How can we actually design a single stub based on shunt or based on series stub? It can be open or short circuit, as you can see from here. Let's look at an example in order to understand better. Okay, for this example, I will be designing a short circuit single stub shunt matching, okay, which means that this part will be short circuit. Let's study a little bit more regards on this example. For a load impedance, okay, so basically we have a load impedance ZL, which is 60 minus J80 ohms. Okay, so basically this will be the load. Basically, they will have this impedance 60 minus J80. Okay, basically the idea is how can we actually design two single stub, okay, which is short circuit shunt tuning network to match this load to a 50 ohm line. Okay, which means that this characteristics is actually 50 ohm. And over here, we have this ZL, which is 60 minus J80. Okay, assume that the load is matched at 2 gigahertz and that the load consists of a resistor and capacitor in series. As you can see from here, basically this will be the resistor, this will be the capacitive effect. They are connected in series. Okay, plot the reflection coefficient magnitude from 1 to 3 gigahertz for each solution. Let's do step by step how can we actually do this example. Okay, so this will be the load impedance. What we are going to do is we are going to normalize this with respect to the characteristic impedance. So over here, I can see that the characteristic impedance is 50. So basically, the load impedance will divide by 50, and I actually get this outcome. Okay, so basically, this will be the normalized value, which is 1.2 minus J 1.6. Okay, so I can easily find the admittance of the load, okay, by doing a 1 divided by over here, and this will be 0.3 plus J 0.4. Or I can actually find the admittance of the load by doing it at the Smith chart, which I'm going to show it to you on the next slides. Next, I will also be able to plot this VSWR circle at the Smith chart. Okay, so this will be the Smith chart. Okay, if you still remember, okay, the load impedance, okay, I actually after normalize, I actually got this answer, which is 1.2 minus J 1.6. Okay, how can I actually draw this 1.2 minus J 1.6? Okay, take a look over here. Okay, so this part here will be 1.2. And this part, because it's minus, so therefore I know that it's underneath this center line of the Smith chart. So I actually look for 1.6, and basically the two intercept point, this will be the ZL. Okay, once I get the ZL, I can easily find my admittance of the load also. How can I actually plot this point here? So I have this point, and basically I cut through the center point of the Smith chart, and basically I extend this part here. Again, okay, I also will be able to draw my VSWR circle. So what I'm going to do is basically I put my compass, okay, one point here and another point here. Then I will be able to draw this circle. Okay, so I guess you understand what I mean. So I just put one point here, another point here. So I will be able to draw this circle. So basically the so-called the point that actually intersect, this will be my admittance load, which is 0.3 plus J 0.4. Okay, so now let's do the single stub design. Okay, so there are actually two solutions you can see from here. Okay, so if you notice that the VSWR circle actually intersect the 1 plus JB circle at 2 points. Okay, so basically this will be the 1 plus JB circle. Okay, so there are 2 points that will be intersect. Okay, let's discuss the first point here. So basically, I actually move to this direction here. Okay, why I can only move to this direction is because, okay, let me explain this. Okay, so this is YL. Okay, YL is actually over here. So the distance D is basically I need to so-called move towards the generator. I need to move towards the generator. If you take a look over here, you can see that basically clockwise will be moving towards the generator. So therefore, my YL position, which is over here, I need to move towards the generator. So therefore, I can only move in this distance. And basically, this will be the first point that actually intersect the 1 plus JB circle. Okay, so basically, this is the idea. Okay, so therefore, this point here, I can only move so-called at the clockwise direction until it touch the 1 plus JB term. Okay, so basically, this will be the distance which we know as D1. Okay, another set of solution, as I mentioned here, there are actually 2 points. Okay, another solution is basically you can see from here, I actually went through the first point. After that, they actually touched to the other point. Okay, if you still remember, okay, YL, I basically can only move towards the generator, which means that it's actually a clockwise. So basically, I need to find the distance from here to here. This will be known as D2. Okay, so basically, I have earlier on, I find this from here to here will be my D1, and from here to here, okay, will be my D2. Okay, so let's do a very simple understanding on this here. So now let's focus on the first scenario. Okay, so this will be the first scenario here. If you still remember, okay, so this will be the first point that we need to calculate. I need to know what will be the length of D1. How can I actually obtain the length of D1? Okay, if I zoom at the Smith chart over here, okay, which is further magnified over here, you can see that they basically cut over here. As you can see that this is 0.06, this is 0.07. You can see that this will be 0.062, okay, 4, and then 6. So therefore, I have this 0.066 lambda here. So next, I will be, again, need to know how much it cut over here. So let's zoom in over here, okay, which is illustrate here. So from here, you can see that this part is 0.17. Okay, this will be 0.18. So 17, 2, 174, and then closer to 176. So I just so-called round off and take it as this will be 0.176 lambda. Okay, remember the distance D is basically from here to here. Okay, so how can I actually get this from here to here? This number start from here 0, and then finally they reach over here, which is 0.25. So in order to get the distance D, what I need to do is simply I take this 176 over here, okay, minus away this 0.066 lambda, then I will know my distance D1 or the length D1, which is 0.11 lambda. Okay, so basically this is how I obtain the first D1. Next, as I shared with you earlier on, I actually has two solutions. Okay, so let me work out on the second solution. So now I need to find the distance D2. Okay, which is from here to here. Okay, earlier on is basically D1 is from here to here. So now I need to find D2, which is from here to here. Again, how can I find the answer? Okay, so this I have illustrated. So this point here, I already illustrate that this is actually intercept at 0.0066 lambda. So let's magnify over here. Okay, so if I magnify over here, you can see that this is 0.32, this is 0.33. So this will be 0.322. This will be 0.324 lambda, which is illustrated here. And again, I need to find the distance D2. So how can I actually find the distance D2? Okay, I will be using this number here, minus away this 0.066 lambda. Then I will be able to find my distance D2. Okay, so over here you can see that I managed to find the distance D1 and also the distance D2. And I actually propose the two solutions here. The first solution, okay, will be 0.110 lambda. And the second solution will be 0.5258 lambda, okay, which is from here. And the first solution is actually from here. And therefore, the first step I have finished is basically I have calculated the distance, okay, between the loop and also the start position. Okay, these are the two solutions. The first solution, I have 0.110 lambda. The second solution, I have 0.258 lambda. Okay, so this will be the two solutions. Okay, as mentioned earlier on, this example actually illustrate on a shunt stub. And basically this part here will be short circuit. Okay, keep this in mind so that I will continue my discussion. How can we actually design the length of this so-called stub? Okay, before I continue, I urge you guys to help this video by like and also subscribe to this channel. Thank you so much. Let's move on. Okay, so earlier on, okay, I have calculated this. This will be one of the points that intercept the 1 plus JB. Okay, basically the circle here. So let's focus over here. Okay, how can we actually obtain? Okay, basically what you need to do is from here you can see here. Okay, I actually draw onto the imaginary part here. Okay, so I get this answer here. Okay, so basically the point I have mentioned here. So next, okay, what I'm going to do is, okay, I draw a line that cut into here. Okay, so basically once I cut over here, I'm ready to work onto this solution. Okay, so again, if you zoom in over here, okay, so this will be the distance, okay, L2. So if I, L1, sorry, if I zoom in over the distance here, okay, I will actually find the number which is 0.152 lambda. Okay, so basically this will be the 0.152 lambda. Okay, so next, okay, remember this part here, okay, if you look at this Smith chart here, you can easily see that, okay, for impedance, okay, so this will be a short circuit, this will be an open circuit, but once we go into admittance, this will become an open circuit, this will become a short circuit. As I mentioned earlier, we are going to do the shunt, okay, with short circuit. So therefore, I can actually start from this point here. Okay, but for this case here, okay, we can't move towards the generator now, okay, because we are going to move towards the load. And we actually move towards the load, we need to do counterclockwise. We need to do counterclockwise. So now I need to find the distance L1 for this particular length here. What will be the length of L1? Okay, so I need to find this. How can I actually find? Okay, so this part here, okay, quite easily is basically, as I told you that this is 0, they go all the way to here, okay, will be 0.25, and if I know that this is 0.152, I easily can find my so-called L1 from here to here, okay, by taking this 0.25 lambda minus 0.152 lambda, so therefore my length 1 will be equals to 0.098 lambda. Okay, so the length for the first case I done, I managed to find it, which is 0.098 lambda. Next, okay, let's focus on the second solution here. Again, from here, okay, I can actually draw this part here, okay, which will be my length 2. And what I need to do is basically at the center, I actually cut the point over here. Okay, so basically how much to move again? Okay, I need to move from here. This will be so-called the short circuit at the admittance charge here. Okay, and then I need to move towards the load. Okay, which is this direction, which I need to move towards the load. Okay, and then I zoom it over here. Okay, so this will be the number, which is 0.346 lambda. Okay, which is over here. So if you zoom in here, you should be able to see that this will be 0.346 lambda over here. You can see from here, this is 0.33. This is basically 0.34. Basically, I actually obtained 0.346 lambda here. So how can I actually find my L2 over here? So over here, you know that one full circle will be 0.5. Half of a circle will be 0.25 and the full circle will be 0.5. Okay, and then I need to find this part here. How can I actually find this part? We'll be using this 0.345, okay, minus away this 0.25. So I take away this, I actually will find the length of L2, okay, which is equal to 0.404 lambda. So now I have also successfully calculated my length of L2, and therefore I can present my solution here. Okay, so this is what we have done on the first part. Okay, this will be on the second part. This will be from the second part over here. I get the answer here, 0.098. Okay, so which is shown over here. Okay, 0.098. This will be earlier on, this part here, 0.404 lambda. Okay, so therefore this will be my proposed solution, my first solution, and my second solution. Okay, so what is the meaning over here? So basically what I need to do is basically when I look into here, okay, basically we'll have this Y0 plus JB, and what I'm going to do is basically I'm going to cancel away the effect. Okay, and then with the adjust of the length, basically with this, I actually cancel away the effect of so-called the imaginary portion here. Okay, with this, I have successfully designed the single stub matching. Let's do a very quick conclusion. Okay, usually it is very desired to keep the matching stub as close as possible to the load to improve the bandwidth of the mesh and to reduce loss. So the key idea is we want to keep the length as little as possible or as short as possible so as to improve the bandwidth of the mesh, and also this will also reduce loss. So in short, okay, the longer the line, okay, you can anticipate that we're going to have more loss. Okay, and the longer the line, okay, we are going to have lesser bandwidth. So hence this will be undesired. And basically, this will cause a possibility large standing wave ratio on the line between the stub and the load. Okay, at the two intercept point, okay, the normalized admittance here, we actually have these 2 points here. One will be the plus term here, one will be the minus term here. Okay, and then this will be the so-called, you can either plot this, normally nowadays we will simulate this result. So from here, okay, we can observe that solution 1 has a significant better bandwidth than solution 2. Okay, you can see that this will be solution 1. Solution 1 has a better bandwidth as compared to solution 2. Okay, so this is because, like what I mentioned here, the D and L1 are much shorter for solution 1 as compared to solution 2. If you still remember, you can see from here, solution 1, firstly, the D is shorter. Okay, this length is also shorter as compared to the second solution. And hence, because of this, solution 1 will have a better bandwidth as compared to solution 2. Okay, as the length, basically, they are shorter. Okay, which also reduce the frequency variations of the mesh. So with this, I'd like to end my discussion. Please help to like and subscribe. Once again, thank you so much. I hope to see you guys soon. Bye for now.